So our topic today is section 4.4, which discusses linear independence. So this is a property that a set of vectors may or may not possess. So let's start with a definition. So we'll go over the basic definition here. So we let V be a vector space, and S is a subset of vectors. So we'll start with talking about the case of finite subsets, and we'll do infinite ones later on. Now we say that S is linearly independent if you can form non-trivial linear combinations of the vectors inside S. So let's look at this expression here. So now observe that if all the C's are 0, then trivially this is true. So the interesting statement here is it the case that you can find a non-trivial linear combination of these vectors? And if that's the case, then we say that the vector that the set is linearly dependent. And if it's not, then we say that it's linearly independent. So a set, so this is a either-or property. Given any set in a vector space, it's either linearly dependent or it's linearly independent. And it's linearly dependent precisely if you can form these non-trivial linear combinations to form 0. Another way, so something that's logically equivalent to the definition, that's very easy to show, is this claim here. So this you can view as an alternative definition of linearly independent. So in the original definition, we started by defining what linearly dependent means, and then we defined it independent as being just the other case. If you want to directly go for defining linearly independent, then it means the following, that so given a subset S of a vector space, the statement is this, that S is linearly independent if the following holds true, that if you form a linear combination like this that equals 0, then the only way that this can be true is if every Cj is 0. So notice that that implication is trivial. So going from the right to the left is not interesting. It's the case of going from left to right that has meaning here. So that is the definitions. You can use either one of these definitions of linear independence. So let's do some examples. So we start with a very basic one. We take the vector space to be R2 here, and then you take just the two unit vectors. So this is pretty much as simple as it gets. We're going to answer the question, is S a linearly independent set? So the set S of E1 and E2. So what we do is we use this, let's go back. I'm going to use this definition to verify if it's linearly independent. So say C1 E1 plus C2 E2 is equal to 0, the 0 vector. Now the question is, does this eventually imply that both C1 and C2 are 0? And if that's the case, then the answer is yes. So now if we write this out, well, C1 times E1, that's just the vector C1, 0. And this is just the vector 0, C2. So that statement is the same as saying that this holds, which is the same as saying that this holds. And that, of course, holds if and only if both C1 and C2 are 0. So yes. The answer here is yes. S is linearly independent. You cannot form a linear combination of E1 and E2 that works out to be 0. Okay, so in this case, you could really just look at it. Once you internalize the definition, it's obvious that E1 and E2 are linearly independent. So let's take another case. So let's move on to this example. So now we're given two vectors v1 and v2. I see I forgot the subscript. So let's do the same thing. So say c1 v1 plus c2 v2 is equal to 0. Now that we can write as a matrix equation. So this is stuff you're very familiar with. So this equation, right? So this equation here is equivalent to this equation here. And now we know exactly what to do. We just use row elimination. So we write that system as follows. We row eliminate, so we take -2 times the first row and add to the second. We get... And now we see that there is a unique solution to this. Because we have these pivot elements. We have a pivot element in each column, so there is a unique solution. And that one is, of course, just the trivial one. So again, yes, this is a linearly independent set. Now let's move up to R3. So we'll start with another very simple example. So we're given the vectors v1 and v2. We form the set containing both v1 and v2, and the question is S linearly independent? So we proceed just as before. So I'm guessing many of you will now have started to see what the pattern is. There's of course a general algorithm that underlies all this, but let's go slow. So now we have this extended linear system. I eliminate, I multiply the first row by -1 and add to the last, and then I get this linear system. Again, we have a pivot element in every column, so unique solution. So the only way to have this be true is if both C1 and C2 are 0. So this is a linearly dependent set. Did I say independent? I meant to say linearly independent set. All right, so let's go to the next example. So now it's starting to get a little bit more computationally non-obvious. So now we have a larger linear system like that. So let's write this out. 1, 1, 2, 2, 3, 3, -1, -3, 0. Now we'll do row eliminations. I'll go a little bit fast here because this is stuff you've seen a million times. So I subtract the first row from the second. I get 1, 1, and then -2, right? 0, -1, 2. Is that right? Yes, I think that's right. First row is unchanged, and now we see that something slightly non-typical happened in that the last row just cancelled. So in this case, it looks like we will have non-trivial solutions. And if we just go back and eliminate that 2, then we get 3. Okay, so now there are non-trivial solutions. So we have C3 as a free variable, so let's just set C3 to be 1, and then the first equation reads as C1 plus 3C3 is 0, so C1 would be minus 3. The second equation reads as C2 minus 2C3 is 0, so C2 would be 2. So the solution set then is 1, 2, minus 3. So we find that if you take 2v1, no, that was wrong. If I take minus 3 v1 and I add 2 v2 and 1 v3, then this works out to be 0. Okay, so here is C1, here is C2, and then C3 is just 1. So in this case, the answer is no. S is linearly dependent in this case, because I could form this non-trivial linear combination here, right? So this statement tells us that this set is linearly dependent. Now let's consider more general cases. We'll start by just considering a general situation in R3. So suppose we're in standard three-dimensional space and we're given a set of n vectors. Now let's think about the different situations. What could happen? So if there's just one vector in the space, then you find that it's very easy. As long as v1 is non-zero. As long as v1 is not the zero vector, then S is linearly independent. Because you have nothing to work with. If you're given one non-zero vector, clearly you cannot form any non-trivial linear combinations. If you have two of them, then the statement is that they need to be not parallel. So if, right, so that actually goes both directions. So if v1 and v2 are not parallel, if they do not lie on a line, then S is linearly independent. If you have three of them, then the statement is that they cannot all lie in a plane. So you remember this is exactly like we're really just going over when does a in this case a 3x3 linear system have non-trivial solution, and it's if the three rows, or equivalently the three columns, do not lie on a plane. This is equivalent to S is linearly independent. What if you have four of them? In that case, so let's think about it. So if you form the extended linear system here, it's going to look like this. Right? So now it's impossible to have a pivot element in every column. You must have free variables in this case. So in this case, it will always be linearly dependent. It's impossible in R3 to form a set that has four different vectors that is linearly independent. Okay, so now that we've gone through R3 carefully, you see that you can easily extend this to m dimensions. So remember the concept that's really helpful in classifying when you have non-trivial systems to a homogeneous linear system is this notion of rank. So we form the coefficient matrix. So you take all these vectors Vn, like so. This is an m by n matrix. And then let K denote the rank of A. Do you remember rank? That if you take A and you form the reduced row echelon form, or even just the row echelon form, then the rank is the number of pivot elements. And if there's one pivot element in every column, then there's a unique solution. In this case, that's only the trivial solution, and that's when you have linear independence. So now the statement is that, maybe do this in red because it's important. So now S is linearly independent if and only if the coefficient matrix has full rank. A has rank K equal to n. So in particular, if n is larger than m, then the rank of A, it's certainly smaller than m. You cannot have more pivots than you have rows, which is less than n. So in this case, S must necessarily be linearly dependent. Okay. Let's consider some examples with polynomials. So question here is always the same. Is S linearly dependent? Or let's formulate it as independent. Well, so the first one is easy. So say C1 times 1 plus C2 times x plus C3 times x squared is equal to 0. Well, the only way to have this polynomial be 0, notice I'm not solving for x here, I'm considering this as a function. And the only way that the polynomial C1 plus C2x plus C3x squared is 0 as a function is if all these coefficients are 0. So yes, this is a linearly independent set. Okay, so the next example is a little bit more interesting. So let's consider this one. So if I take C1 times the first guy and C2 times the second and C3 times the last, then now the question is, do I have non-trivial solutions to this? So what we need to do here is we need to collect the coefficients. Okay, so that has to be 0. This is the coefficient for the constant function. Then what's the x? We have C1 plus 3C2 minus 3C3 times x. And then for x squared, we have 2C1 plus 3C2. So that has to be 0. So now I can write this as a linear system. Let's see, so that we get this right. So 1, 1, 2. These are the coefficients that multiply C1. So 1 from there, 1 and 2. And then the coefficients that multiply C2 are 2, 3, and 3. And then we have minus 1, minus 3, 0. And now those of you who have strong memory will recall that this is exactly the linear system we had a couple of slides back because I'm lazy. So you see it's the same as this one, the second example here. So this is row equivalent to 1, 0, 3, 0, 1, minus 2, 0, 0, 0. So the non-trivial solution now is C1 is minus 3, C2 is 2, and C3 is 1. So what this tells us is that right? That minus 3 times like this. So in this case, the answer is no. This is a linearly dependent set. And at this point, you might start to suspect that there's this set, if you think about it, this set P2. It certainly seems like it's awfully similar to R3, doesn't it? Because this computation we did is exactly the same as the computation we did for R3. And this is really one of the concepts that we're going to explore in chapter 4. This connection between all sorts of different vector spaces and Rn. All right, so now let's talk a little bit more, a slightly different approach to this notion of linear independence. So let S be a set with at least 2 elements. Then we have the following statement, that S is linearly dependent if and only if you can write one vector in S as a linear combination of the others. And when I say one, I don't mean that there's only one, there's at least one. Typically, you can take any of them and write them as a linear combination of the others. But the statement is that there has to be at least one such that you can write it as a non-trivial, as a linear combination of the others. So let us prove this. So we start by going in this direction. So we assume that S is linearly dependent. Then there exists coefficient Ci, not all 0, such that I can write this. So I can form a linear combination that's non-trivial to form the 0 vector. And now, say C1 is non-zero. Then I could just move all these guys over to the right and divide by C1, and I would get that V1 is expressed as a linear combination of the others, right? So now the only complication, and this is really just notational, is that C1 could potentially be 0. So that's not what we're going to do. We have to be a little bit more complicated here and say that, well, we know that at least one of these CJs has to be non-zero. We know that there is an index I such that Ci is not 0. So then let's call that equation star. And from star, we'll pull out Ci, Vi, and then write this like that. And then now we can just divide by Ci to get that Vi is sum over all indices j that are not equal to I. Okay, so there we have our linear combination. So now under the assumption that S is linearly dependent, we've now expressed one of the vectors as a linear combination of the others. So let's go in the other direction. So assume that we can write vector I as a linear combination of the others. So in other words, we assume that we can write Vi as a linear combination of the remaining vectors. Then let's just move Vi over here. That didn't look super clear. Let's use a different color. So now what I'm going to do is I'll move Vi over to the right, and then I get that 0 is minus Vi plus sum over j not equal to I Cj Vj. So now I've formed a non-trivial linear combination of the vectors that all add up to 0. So we see that S is linearly dependent. Now, so you have to be a little bit careful about this statement that you cannot identify in advance. I cannot say that I can necessarily write V1 as a linear combination of the others. There might be something that sticks out. So this is important. So say let's make clear this is not part of the proof. So if you're in R3, you may have V1, say this is 1, 1, 0, and V2 is 2, 2, 0, and then V3 is 0, 0, 1. Then notice an S then is the set of all these. Then I have V1 is equal to 1/2 times V2. I have that V2 is equal to 2 times V1. So I can write V1 and V2 as linear combinations of the others, but V3 you cannot write as a linear combination of the others. So be careful with this. It's not the case that you can write any arbitrary vector in the set as a linear combination of the others. It's just that there must exist at least one. So this leads us, let's continue on this trend a little bit about writing vectors as linear combinations of the others. So first of all, we have to define a couple of things. Let S be a subset of a vector space V. Then first we're going to define what it means to subtract an element from a set. So it's this notation here. So V is an element in S. And then if I subtract V from the S, I write that as S minus the set V. So it's really, I'm redefining the minus symbol here. Sometimes people use a backslash, but yeah, it really just means take a set and remove one element in the set. Then the important thing we're doing here is introducing this notation redundant. So we say that a vector is redundant if it's the case that the span of the set S is the same as the span of the set S with a vector V removed. So what this means is that V doesn't really contribute. If you take the set of vectors and you consider the span of these guys, then there's a vector that doesn't contribute. Should have maybe done an example. Let's do an example. So say we're in R3, V1 is like this. So these three vectors, they all lie in the xy plane, in the x1, x2 plane, I suppose. And I can pull out any of them. Any of these vectors are redundant because v3 I can write as a linear combination of v1 and v2. So if I eliminate v3, I get this, the span does not change. The span will remain the x1, x2 plane. You can do the same thing if you pull out v1, then you could then write v1 as v3 minus 2 v2. It should be a minus. So you can delete any one of these three vectors and get the same span. You can't delete two of them. So there's one redundant vector, but there are not two. So this is what the concept of redundance means. So now you see that you can redefine, now that we've defined the notion of redundancy, then you can use a slightly different definition of linear independence. If you like, we used to say that in a linearly independent set, there are no redundant vectors. So it's just another way of defining or verifying, if you like, whether a set is linearly independent. So in a linearly dependent set, there's at least one redundant vector. In a linearly independent set, there are no redundant vectors. Okay, so now we can formulate a Lowe theorem, which is yet another classification of linear independence. So it says the following, that if S is a subset of a vector space V, then S is linearly independent if and only if the following two conditions both hold. So first of all, V1 has to be not the zero vector. And then it's the case that as you look at successively larger sets, so this is a recursive definition. So it says for k equal to 2 that V2 is not in the span of V1. So now V1 and V2 are necessarily linearly independent. And then for k equal to 3, it says that, well, V3 does not lie in the span of V1 and V2. And then it says that V4 does not lie in the span of V1, V2, and V3, and so on. So these statements are both equivalent. So if these two statements on the right hold, then necessarily S is linearly independent. The proof here is very straightforward. I mean, if you think about it, suppose, let's just talk about it quickly, and then you can fill in the details for yourself. So, I mean, what I would do is to say you go in this direction, you could assume that S is So assume that S is linearly independent, then, well, clearly it can't hold any zero vectors. So the first condition holds. And then, well, if you see that this condition fails at any point, if you can write Vk as a linear combination of the previous ones, then that means precisely that you can form a non-trivial linear combination, and that's impossible because S is linearly independent. To go in the other direction, you can do this in different ways, but you can assume S is linearly dependent. So this is the converse of the assumption in the first. And in that case, you know that there exists a non-trivial linear combination. And then clearly at some point, you have to be able to write one vector as a linear combination of the previous ones. So it's a very straightforward proof. So work out the details for yourselves. We'll do that as a little extra exercise. Then this is important. So suppose that S is a non-empty subset of a vector space V. Then if S is linearly independent, then it turns out that you can write that if you take a vector in the span of S, so span of S, remember, it's a set of all linear combinations. And the important property here is that if S is linearly independent, then the way you write things as a linear combination, it's unique. So when S is linearly independent, then there's one and only one way of doing this, that every Cj is uniquely defined by this expression. And why is this? So again, we'll just sketch the proof. So this is really quite straightforward. So say you have a vector v that's written as a linear combination like this, and then suppose that v can also be written as like this. So in the first one we use expansion coefficient Cj, and in the second one we use Dj. So now if you combine these, this means simply that C1, if I subtract one from the other, well, maybe we should do that step. So we get the following expression, and then if we just put them all on the same side, we get this. And now you see that if the VJs are linearly independent, then that means that all these differences have to be 0. So the coefficients are uniquely defined. That's really what this means. And conversely, if they are linearly dependent, then there exists some non-trivial linear combination, and you can find two different sets of expansion coefficients that both result in the same vector. And the very final thing we will do in this section is to talk about what happens for infinite subsets. So the notion of linear dependence and linear independence, it can be extended to infinite subsets. And the definition is, at least superficially, extremely simple. It's simply to say that if you're given an infinite subset, then we say that the infinite subset is linearly independent if every finite subset of S is linearly independent. And you see that a lot of the concepts we've gone over so far carry over straight away to the case of infinite subsets. So we'll do some examples in subsequent sections where we'll see that a lot of these things work very well for infinite subsets as well. The only one we'll do now is we'll move on. So one of the few, so the only examples we've talked about that involve infinite subsets that could potentially be linearly independent are the function spaces. So the set of all polynomials, for instance, does have infinite linearly independent subsets. If you take the set of all continuous functions, for instance, that would be on the real line, that would be another example of a subset that contains infinite subsets that are linearly independent. So for instance, if you take the set of all polynomials and then you have all the even powers, then recall that span S is the set of all even polynomials. And it's obvious in this case that S is a linearly independent set, because if you take any subset of S that's finite, then clearly that's a linearly independent set. And then directly by just invoking the definition, you see that that means that S itself is linearly independent. And that concludes this lecture. So we will continue on Thursday with section 4.5.